This is Lesson 5, Part 1, Network Security Implementation. The learning objective for Lesson 5 or Chapter 5 is to describe network security implementation strategies and the roles each can play within the security life cycle. The key concepts are why layered security strategies help mitigate risks, threats, and vulnerabilities, layering security to provide enhanced security for enterprise network resources, practices for hardening systems and networks against an attack. Security is a process or life cycle that requires constant attention and identifying security concerns of local, remote, and mobile employees. Here we see a diagram of layered security with our network at the core of the layering. It's a network that the attackers are trying to hack into or attack, and surrounding the network are antivirus software, vulnerability assessments that must be conducted, an IDS or IPS, intrusion detection system or intrusion prevention system, a firewall outside of that at the edge of the network, probably the local area network, and then security policy, which a lot of people do not think is the overriding concern, but all of these other technical implementations must have a security policy that describes them, defines them, and gives us the processes needed in order to implement these various different components of our security. Layered security in action. You know that known exploits target your web server. The firewall is configured to allow web traffic. Again, a firewall that isn't configured properly is not going to work the way you want it to. Just because you have it doesn't mean that it's going to do what's necessary. An intrusion detection system, which detects the exploit. A vulnerability assessment, which informs no action is needed because the server is not vulnerable. If you had a zero-day virus emailed to a user, the firewall is configured to allow email. The intrusion detection system may not have the signature for the new virus. The antivirus is a heuristic engine that identifies possible virus-like activity. The analogy for layered security are concentric castles, which provide a superior defense of two or more perimeter walls, an outer wall and an inner wall. Collapsible defense, designed to secure the keep, which would be at the center of the castle, and the focus was on the perimeter security on the outside edges of the castle and at each layer inside of it. In a network security application, you have an external firewall that functions here between the internet and the web server, then an internal firewall as yet another layer, if you will, between the web server and the DMZ, perhaps, and an internal server, then another internal firewall between the internal server and the laptops and workstations. So the idea here is that you want to ensure that you have as many layers as possible between your trusted network and the untrusted internet. And again here, another description of it, similar to a demilitarized zone. You have the two or more firewalls. The idea is to secure the internal network and, of course, these various layers of perimeter defense. Here, improving concentric castles, they relied upon walls as barriers to entry and added additional barriers such as moats. Additional defenses such as a ranged defense of archers or vats of hot oil back then. The archers could be moved from one part of the castle to the other. And then a melee defense, in other words, knights and swordsmen who would attack or defend the castle in groups, if you will. And so the idea, of course, is that this is analogous to how we would defend a network. We want to build upon layered security. Layering only provides breadth. The depth is the overlapping countermeasures at each layer that can be from multiple vendors. If one is good, two must be better, they say. Different antivirus patterns, for example, equals a higher chance of detection. So here we see in this example, antivirus defense in depth is that the desktop antivirus is from vendor A and the email antivirus is from vendor B, and that gives us defense in depth in this situation. The bigger picture, of course, is that the firewall typically sits between the LAN to WAN domain and the WAN domain, the system application domain. So we have the external and internal firewalls, and then the antivirus software that would be on a server and on a desktop, and they possibly would be different. And then the IDS and IPS can reside at the network level, but they need to be placed in the right locations on the networks for this to work. Or the host level, but again, they need to be placed on the right hosts. If you're going to have it on selected hosts, you need to make sure that you choose the right ones. There are a lot of hosts in a network, and you can't put an IDPS or IDS IPS on each one, so you have to make sure that you correctly select the ones that need them. Network security, some key components. The primary objectives, of course, confidentiality, integrity, and availability. A security policy, the layered security plus defense in depth. Network design, the protocols, topologies, addressing, and communication. And of course, your equipment selection is going to be important. You have to harden your system. Of course, authentication, authorization, and accounting are important. Authentication, who is allowed into the network. Authorization, what can they do when they get into the network. And accounting, do we log them? Do we keep track of what they do once they're inside the network doing what they're authorized to do? Encryption, redundancy, of course, having duplicate servers, duplicate systems to prevent a single point of failure, and endpoint security. Some concerns here, addressing, we have private and public addressing, as well as static and dynamic. Of course, the private and public would be separated or differentiated by perhaps a network address translation. NAT would be used to keep the public IP address different from all the private IP addresses behind it. Our topology, whether it's a ring, a bus, a star, a line, which is similar to a bus, a tree, full mesh or partial mesh, which full mesh allows all of the nodes to communicate, but of course, as we know from the way it's calculated, it becomes a nightmare in terms of how many connections there have to be in order to have a full mesh network. And of course, a partial mesh, but that may not allow full connectivity. The protocols, there are many different protocols to consider. Most networks use TCP/IP and IP version 4 as opposed to IP version 6. IP version 4 typically defaults to a plain text form of transmission, while IP version 6 can be set to encrypt transmissions. So some other things to consider. Is the current protocol easy to compromise? Are there numerous exploits for this protocol available for novice hackers? Will encryption interfere with other technologies such as NAT or IPsec? Things that you have to really think about. You also have to evaluate every single protocol across every theoretical layer of the OSI model network protocol stack. For example, do you still want to continue to use SMTP and POP3, the simple mail transfer protocol, and the post office protocol? You have to consider communication that goes outbound and communication that comes inbound. And again, redundancy is so important to a network because, again, we want to try and avoid those single points of failure if as much as possible. Public addresses have a finite number of addresses available issued by the Internet Assigned Numbers Authority, or IANA. They're controlled at the regional level by regional registry entries, and of course regional means as big as or as large a region as an entire continent. They have direct communication with the Internet and are required for Internet-facing applications. Your business can't be found if you don't have a public address, but the internal addresses can be secured or can be hidden by network address translation by NAT. Private addresses. You have a reserved IP space, so your Class A addresses are 10.0.0.1 to 10.255.255.255. Your Class Bs and your Class Cs. Most organizational sites, typically, because of the number of nodes they have to be at, unless they're subnetted differently, are going to be as large as a Class B address. here at Armstrong State University, we begin with 130.254. Well, that's a Class C would not be enough, would not provide enough nodes for the entire network. So of course it has to be, and we may only have like 1,000 nodes. We're not as big as the University of Georgia, but we could not get by on a Class C network, and so 130.254 as our prefix, or our first 2 octets, is going to be make the university into a Class B network. They can be reused on internal networks and isolated from the internet. You may need to use network address translation to communicate with the internet. Static addressing. Each system is configured with an address. The static addresses are assigned at the device level. Systems are manually configured with an IP address, and a central authority does not exist. Each system is guaranteed the same address, but making changes in the static addressing can be very cumbersome. Dynamic addresses are assigned dynamically from a central system. You request those IP addresses from that system. They use the Dynamic Host Control Protocol, DHCP. The systems may acquire a different address. Reservations for the same address can be made. The addressing is centrally controlled. An attacker, though, may be able to borrow an address to conduct the attack. And lastly, we want to talk about physical security. Physical access may bypass many other controls. Critical devices should be stored in an isolated data center. That's a typo there. It should be stored in an isolated data center. In any case, you need to have multi-factor physical authentication, and you have to limit the staff with access. Not everybody needs to get into your server room, and only those who need to get in there should have the authority should be authorized to do it. Once they are properly accessed into the network, that doesn't mean they need to be authorized to go into your server room, for example. They need to have fire suppression, because fire is the #1 physical threat to all computer systems. They need to have CCTV cameras where appropriate, if you really believe that you need to ramp up your security by being able to record who goes in and out of a computer room or a server room and what they do. And you need to compensate controls for mobile devices. These compensating controls need to include encryption and perhaps anti-theft tracking software. Okay, so that concludes part 1 of chapter 5, and we'll talk about authentication and authorization in part 2.